So let's say you need to figure out the average height of every adult in a country. You can't possibly measure everyone, right? So how do you make a really smart guess from just a small sample? And more importantly, how do you deal with the fact that you don't have all the information? That's exactly what we're going to break down today. Here's our game plan. We'll start by digging into why this is such a tricky problem. Then, I'll introduce you to the special tool we use to solve it. After that, we'll walk through how to build a confidence interval, see it work with a real example, and finally, figure out how you can plan your own studies. All right, first up, the uncertainty problem. Before we get into any formulas, we really need to get a handle on the core challenge we're up against when we're trying to guess an average. This is the big question, isn't it? You take a sample because it's all you can do, but how sure can you be that the average of your little group actually represents the true average of the entire population? That's the puzzle. So where do we even begin? Well, the most logical starting point is the average of our sample. We call this X bar, and it's our single best guess for the true population average, or mu. It's simple, but, it's just one number. And here's where things get really interesting. In the real world, you almost never know the true standard deviation of the whole population. That's sigma. All you have is the standard deviation from your little sample, S. And using S instead of the real sigma adds a whole new layer of uncertainty that we have to deal with. So how in the world do we account for that extra uncertainty in our math? Well, that brings us to our hero of the day, the t-distribution. It was literally invented for this exact situation. Yep, enter the student's t-distribution. When that population sigma is a total mystery and you're stuck using your sample's S, the t-distribution is your go-to. It's just a more realistic, a more cautious way to approach the problem.
Now, at a quick glance, it looks a whole lot like the normal bell curve we all know. It's symmetric, centered at 0, but the secret sauce, the thing that makes it so perfect for our problem, is that it has heavier tails. So what does that actually mean for us?
Well, the shape of the t-distribution isn't just one size fits all. It actually changes based on something called degrees of freedom, which is just your sample size minus 1. Think of it like an uncertainty dial. The smaller your sample, the fewer degrees of freedom you have, and the flatter and wider the curve gets to reflect that uncertainty. And this is the absolute key. Those heavier tails aren't a bug, they're a feature. They literally force our confidence interval to be wider, giving us a bigger safety net. That wider range is how we mathematically account for the fact that we don't know the true population sigma. It's being more honest about our uncertainty. And here you can see just how big a deal this is. Look at this comparison with a tiny sample, just 5 degrees of freedom. To get 95% confident, the t-value is over 31% bigger than the usual z-value you might use. That's a huge difference, and it directly makes our confidence interval wider and, frankly, more trustworthy. Okay, so we've got our tool, we know why it's the right one for the job. Now, let's get into the nitty-gritty and look at the actual blueprint for building a confidence interval with it. But first, before we start plugging in numbers, there are 3 quick checks we need to do to make sure our results are valid. We need a random sample. Our sample can't be too big, no more than 5% of the population, and either the population itself needs to be normal, or our sample just needs to be big enough, which usually means 30 or more. If you've got those, you're good to go. And here it is, the formula. I know, formulas can look a little intense, but trust me, this one is just made of a few simple logical pieces. Let's break down exactly what each part is doing. It's really just a 4-part recipe. We start with our best guess, the sample mean. Then we figure out our adjustment factor. That's the critical t-value. We multiply that by the standard error, which measures our sample's wobble. That all pieced together gives us our margin of error, kind of like a buffer zone, that we add and subtract from our best guess. Okay, enough theory. Let's be real. The best way to get comfortable with a formula is to see it in action. Let's plug in some actual numbers and watch it work. So let's pretend we've done our study, and the average we calculated from our sample, our X-bar, is 52.4. And we also calculated the standard deviation of that sample, our S, which turned out to be 8.3. And finally, we talked to 35 people for our sample. That's our N. And notice, since 35 is bigger than 30, we've met one of our key conditions. All right, let's put it all together. With a sample of 35, our degrees of freedom is 34. Let's say we want to be 95% confident. We look up the critical t-value for 34 degrees of freedom, and it's 2.021. We plug that, our standard deviation, and our sample size into the formula, and we get a margin of error of about 2.84. Now for the easy part. We just take our sample mean, 52.4, and we add and subtract that margin of error. And there it is, our final result, a 95% confidence interval that runs from about 49.56 up to 55.24. So we can say we're 95% confident that the true population mean is somewhere in that range. That's great for after you've already collected your data. But what if you're designing a study from scratch? How do you even know how many people you need to survey to begin with? Well, you guessed it. There's a formula for that, too. This one actually lets you work backward. You decide ahead of time how precise you want to be. That's your E, your desired margin of error. And the formula will tell you the minimum sample size N you need to get there. And this really leaves us with the final and maybe most important question that goes way beyond the math. The statistics give us these incredible tools to pin down our uncertainty. But it's up to us, as the researchers, the decision makers, to decide what level of certainty is actually good enough to answer our biggest, most important questions.